found my camera. That was scary for a minute there. I nearly didn't get to put out a video, which would have been a tragedy. I changed my mind on what I want to do. No more logic for the time being. I want to do a physics one, and I'll do something basic and nice, and I hope you understand this, and it's got a practical in it that you can do for yourself at home. So enjoy. Oftentimes, when studying a physical system and analysing it mathematically, we come across these things that don't change with time under certain conditions. These are called conserved quantities. They stay the same given that certain conditions are true. So, in a closed system, we know that energy doesn't change in time. It stays the same. So, you have the sort of potential energy of things that are gravitationally attracted to each other. You have the speed at which they're moving, and things like that. And that will stay the same. Its energy, the total energy of everything added up, will stay the same. Another one that you might have studied if you've done a little bit of mechanics is momentum, linear momentum specifically. Under no forces at all, its momentum will stay the same. In fact, forces are defined by the rate of change of momentum. So if you have something that's why something going through space just goes in a straight line. Its momentum is defined as its mass times the speed it's moving in a particular direction. The third one, that is one of the most common, and it's the one I want to talk to you about today because there's a practical involved, you can go have some fun, is angular momentum. Now this is defined as the mass of something times the velocity which is moving around a certain point and the distance away from that point, all multiplied together. Mass, velocity, radial distance. We're going to ignore the mass for now, it doesn't really matter. But this is something that happens in a system in which you don't push it around. So if you have a ball on a string and it's going round like this, and there's nobody, as long as there's nobody slapping it as it's going round, and as long as it's in a vacuum, it will still keep spinning. But if you had it running through your hand, say, and you tugged it really quickly, and you probably know about this already just from analysing it yourself with your brain and mind and experiencing it, you know that it speeds up. It gets faster when you tug it. And that's because if you take its velocity and its radial distance, say they're both 2, so it's moving at 2 meters a second and it's 2 meters away from the centre. 2 times 2 is 4. If you were to halve the distance it was away from the centre, from 2 to 1, the 4 has to stay the same, so 1 times something, which is its new velocity, is 4. So we divide 4 by 1 to get 4. We know that it's now going round at 4 meters a second when you halve it. Did you catch that? Go back and watch again if you didn't quite catch that. Now this is where the fun starts, because we all know we're made up of tiny little particles. Well, I should hope you know that by now. You're made up of tiny things. At one level we're all atoms. It does go down deeper than that, but let's just assume we're all just made up of these billiard balls called atoms, small things. If you're in a spinny chair and you're spinning around, then each one of your atoms has a certain angular momentum, and they're going around at a certain speed. The whole system, as a whole, has conserved angular momentum, because they're all interacting with each other radially. I mean, that's the definition. Nothing's pushing it around in a circle. It's all coming in and out. So, if you were to get going in your spinny chair and spin and spin and spin, and you had your legs sticking out to start with, you've got a certain angular momentum. If you pull your legs in, closer towards you, the angular momentum has to stay the same. But all the angular momentum of all these little particles has to stay the same for each one, and you're pulling some of them in towards you, so their velocity has to speed up. So what you find is when you tug yourself in, when you're spinning around in a chair, you speed up. And this is because your angular momentum is conserved. In the same way, if you started spinning around in a chair all tightly tucked in, and then you stick your arms out, and you stick your legs out as well, you find you slow down. This isn't to do with air resistance or anything like that, it's because your angular momentum is conserved. Another thing you can do with this is if you're sitting down in a chair with your legs off the floor and you try to spin yourself around. It doesn't really work unless you try and manipulate some of the friction in your chair or something like that. If you're on a perfectly frictionless chair, you wouldn't be able to rotate yourself around without any contact with the ground because your angular momentum is zero, because you're not moving, and it has to be conserved. There's one way to get around this, of course, is if you take your shirt off and you start swinging it in the air, then you get some air resistance and it starts to turn you slowly. So that's it really. It's a nice little quick one, but the concept of angular momentum is very important. I've talked to some sort of professory people about they didn't believe in time, and they used the angular momentum existing as some part of their argument in that, and it's why galaxies spin around. It's why whirlpools exist, why they keep going round. It's intrinsic. It's nice, and it's a part of the world we live in, and you need to be aware of it, I think. And gives you a nice rounded experience of your life, I should hope, now that you know about angular momentum. Thank you.